So this is all very well, of course, but what if the voltages and the currents are distorted, which is just the stuff we nowadays experience when you just put an oscilloscope in your house, you just try to measure the voltage, and you will generally observe something what we call like a flat top sinus. You have like a third harmonics, fifth harmonic components in there. If you want to do, and the currents, I mean, they are very far from being sinusoidal. So how to deal with this? Well, what I propose and what I tried to do in a couple of years ago was like, I wanted to know, where does this phasor come from? Because the way I introduced it here is was sort of introduced in that way during my own, but it more or less always just came like as it was falling. Like, okay, they came with these plots and they say, well, this is a phasor, just learn how to work with it, and that's it. I was trying to really understand where it's coming from, and as usually. As usual in mathematics, I mean, everything can be generalized, and so is this phasor. So is the Hilbert transformation, and I already mentioned before that mathematicians were calling signals like this complex signals, like analytic representations of a cosine, for example. So analytical signal theory. Well, that is essentially, and I will try to explain this in a few different ways. But essentially what happens if I have just an arbitrarily real signal, so this can be anything, anything as long as I can do the integrals here. In that case, there are always exceptions where these integrals are not signals. That's usually not the case. So let's assume that for any given every given real, like a voltage or a current, let's call it ft, which has some frequency spectrum denoted over here, so the capital F with a hat on it, and then this analytical signal is defined as the positive frequency part of the inverse Fourier transform. So here you have the Fourier transform, and normally you take this from minus infinity to infinity. But now what we do, we take it from 0 to infinity. And we use a little bit of a different factor over here. What we then get is we get our original real signal. We get that just back from this operation, but we get this extra imaginary term, which appears to be the Hilbert transform. And this Hilbert transform in itself can also be defined directly in the time domain. And that's given over here by this Cauchy integral over here, where you see this bar, and that is referring to the principal value of this integral, because you see that at the point where t coincides with tau, and then you have just all like a complex function theory, and with this taking this principal value into account, you just, let's say, hop over the singularity, and everything will be fine. Yeah. If you want to know details, just Google Hilbert transform, and you will see. It's very, very well known transformation in signal processing community, and also in telecommunications, where you have amplitude modulation and frequency modulation and phase modulation and things like that. But I see that from some programs in undergraduate studies, it's somehow removed. I don't know why, because it's still used a lot, and also in like medical sciences, where they have this what is it? This EMRI scans and that kind of stuff. They use it a lot in earthquake studies. They use it a lot. But this is what it is. So remember the positive frequency part of the inverse Fourier transform. So let's have directly an example to show you how it works. So suppose I have this real signal, just the cosine of some frequency, right? It could be the 50 Hertz component, which I now denote by omega naught, because I reserved the omega for the Fourier for the whole set of frequencies. And so the spectrum of this signal in the frequency domain looks like this. So we have two of these Dirac functions which are shifted with respect to this frequency over here. So two of these arrows. Well, if you now invoke this analytical signal transformation to this guy over here, what you get is this. So that's just our rotating unit phasor, right? That's just what we get. That's what this integral is doing to this signal. So what it does is it just shifts this cosine like backwards with 90 degrees or minus pi over 2, and that gives you just the sinus, right? And well, the real signal is Hilbert, the famous Euler equation. That's just our unit phasor, rotating unit phasor again. So, what does this Hilbert transform do to the signal is the following. It's just that it performs this phase shift, right? And then you get like this spectrum for this sinusoidal signal. So if you add these two things, what you will end up with is that and then take the Fourier transform again of your analytical signal, you get this thing. So the way how you can look at recalling this property of Hermitian symmetry, which applies to any real, is that like the frequency, the positive frequency content is exactly the same as the negative frequency content. So there is some redundancy there. So we can drop either one of the two. We can drop all of the positive frequencies and then still have all the information which was there. We didn't throw away information. We only threw away like extra information, too much information, double the information, like half of it we throw away, and then we keep the other part, or the other way around. We throw away the negative frequencies and we keep the positive frequencies. Yeah, we can do that by this. And the only thing is that what we do, if we throw away one part, the positive or the negative frequencies, that means that this property is not fulfilled anymore. And that results in the fact that your Fourier transform is broken and that your analytic signal is no longer real valued. That's where the Hilbert transform comes in. What it essentially is doing is that you very carefully construct an asymmetric or an antisymmetric spectrum to your real to your as such that you kill the negative frequency part. And the cost of that is, of course, that the amplitude will double. That's what I showed previously in the spectrum of this rotating unit phasor, that you saw that this Dirac this component is twice as high. And that's because, of course, you don't want to throw away information, and a particular kind of information is like you want to have that your transformation is unitary, so that the norms, like the root mean square norm, that's an L2 norm essentially, but then weighted over 1 over the cycle, and that is unchanged. That is invariable. That is happening here. So they just add like a smartly symmetric spectrum to your original signal, and then remaining with is your other signal. Yeah. You do. This is what the Hilbert transform is doing. Write it like this. In the frequency domain, it's a very stake. You just introduce the signal function, which is 1 for omega is 0 and is -1 for omega is less than 0. So then the Hilbert transform is just the signal function of the frequency times your original spectrum. It's given over here another example. This is your original spectrum, which clearly satisfies this symmetry property on both sides of the spectrum negative and positive, you just observe the same thing. So then you introduce this spectrum from the Hilbert transform of your signal, and where you just have this part, then the negative of that one, you add them, and this is the spectrum of your analytic signal, which is twice as high because you want to keep the energetic. Okay. What is also interesting to note is that the real and imaginary parts of an Hilbert pair, and that's a very nice observation, and I think that many people don't know this. Also applies to an impedance. So if I have an impedance Z, is let's say R plus JX, right? Then if you know the real part for all frequencies, then you automatically, by applying this notion of this Hilbert pair, then you also know X. And reversely, if you know X, your imaginary part of your impedance for all omega, then you also know the real part. And this is known as the Kramers-Kronig relationship. And Kramers and Kronig, you have the Kramers laboratory at the Delft University of Technology. That was a professor in chemical stuff. And there they also measure impedance of material, and then often they could only measure like one of the parts. I think they most of the time they could just measure the real part, and then they have to make an estimate of the imaginary part. And they did that using this Hilbert pair, but then they did it in the frequency domain, and then their name was is the Kramers and Kronig relationships. Right? You can Google on it. You can find a lot of stuff on the internet. Also, much better explanations than I'm giving over here. It holds in the frequency domain, the time domain, or any domain you wish to consider. But if you know the real signal, you know the Hilbert transform. If I know the Hilbert transform, then I don't know the real signal, just by these pairs. And in between there is just the analytical signal. Moreover, you can also express original signal in terms of your analytical signal only. And that's given over here. Or your Hilbert transform in terms of your analytical signal only, where the star operation here is just the complex conjugate. And recall that this is just a major generalization of what we said before, that if this is the cosine of omega t, then this is just, you can look at this as j omega t, and this as e minus j omega t, right? And here, that's then for a cosine of omega t, or omega naught of t, whatever. And this, the Hilbert transform of the cosine is a sine, and the sine of t, that is e to the power j omega t minus e minus j omega t, divided by 2 times j. So this is like a major generalization of this simple example, let's say. Okay? Well, it's pretty apparent now that the concept of a phasor, but then in terms of an analytical signal, I call it a time-varying phasor, and I will do that in a moment, and that is definitely not limited to simple sinusoid with a fixed amplitude and a constant phase, but it can be applied to much more general signals. For example, if I have a Fourier series of this form, and this you see a lot in articles about power resolution, they usually start from something from like this. And then, well, if you apply the Hilbert transform, and it looks like a very nasty integral with this Cauchy principal value and things like that, but I mean, for signals like this, it's very simple. It just turns out to be this. Yeah. And it's especially so because the Hilbert transform is a linear. transformation. alinear transformation. So when things are linear, then the sum of the parts makes the total. So we can use this here. And again, we have this unitary property that the norms of your original signal are the same as the norm of your Hilbert transform signal. You can easily see it from here. There is no, Hilbert transform only shifts your components by minus 90 degrees, minus pi over 2. That's the only thing what it does. So it's like a filter. In terms of a filter, it's a filter just with a gain of 1, but where the phase shift is like precisely 90 degrees. Think of that. I mean, that people who know a bit about filter realizations already see quite a problem here, right? Because that must be acausal. There's a non-causal operation you perform here. Maybe I come back about that later. There are other issues as well. Well, to give you a bit of a physical, let's say, of a geometric picture, graphical picture, and that if I have the composition of two purely harmonic signals, so of a cosine of t, and I have here a cosine which moves 3 times faster of 3t with a different amplitude. Then what you see here is that if I take the analytical signals of these things separately or individually, then for this one, then this will be my analytical signal, and for this one, this will be my analytical signal, or my rotating time varying rotating phasor, if you like, but at different frequencies. So then you just start. They both have an initial angle of 0, so they all start somewhere about here it starts and there it starts. I freeze it at a certain moment in time, and then I also compute the analytical signal, so of the sum of these two things, and that I call just f. And that at every moment in time, that will just be the vector sum of your original two frequency components here, the original time harmonic signals. So that is what the analytical signal, what it's representing, and what you see that on each moment in time, I have a certain amplitude over here. What you see that this amplitude is changing in time, and also this angle, call it theta, is also changing in time. Well, these two things they rotate at a constant speed. So this just 1 radian per second, and the other one at 3 radians per second. This thing rotates at a time varying speed, right? Which depends. Okay, so that's the essence. Well, these time varying amplitudes and these time varying phases you can define very precisely, and that's done like here. So if this is our analytical signal, so we have a time varying amplitude and a time varying phase, and we designate this omega naught as like the 50 hertz component, or the 60 hertz if you like, just the fundamental, the most dominating frequency. You can also leave it out and then model everything in the amplitude and in this. But for power systems analysis, it can be worthwhile to keep track of this omega naught of your fundamental energy carrier. Yeah, you can write it in this way, like we did before, like in the classical sinusoidal case, and that is just simply our analytical signal. And now this time varying amplitude and this time varying phase is simply defined by this Pythagorean relationship. The same as what you have been doing, like in linear system theory, or just in undergraduate electrical engineering studies, when you were learning how to compute with complex numbers. I mean, this just straightforwardly goes on also in the time varying case. So this is the amplitude, and this is the phase. Where again, This inverse tangent has to be understood, the multi-quadrant inverse tangent, like the tangent 2. So we call this local amplitude and local phase because now we have an amplitude at every moment in time and also a phase in every moment of time. Think about this picture. I get no problem, at least not so far. Here's an example. So here, this is a non-sinusoidal signal. It's actually, this is what we call an amplitude modulated signal, an AM signal, like in the radio technology. So we have a fundamental component. This is like my omega 0. And here I have like a modulated frequency. Let's call it omega 1. Okay. This could like a flicker situation you have you sometimes experience in buildings where just a drop in the amplitude. Well, in green is the original signal. And in red, you see the Hilbert transform. Well, in this case, it's nicely 90 degrees. Yeah, the original one. And you see that the two are, I mean, I should say it's definitely if you take the. So what you see is what now the amplitude is doing, is time varying amplitude. What it's doing, it's tracking modulation of your original signal. That's what it's doing in this case. Essentially, that I deal the signal and I get like the varying amplitude of my original signal, and this is my instantaneous or local phase, which reflects just the points in the cycle. And I mean, this is actually 2 cycles. I mean, here you have T, so it repeats itself. Points in the cycle of local oscillations. Yeah, that's what it's doing. So locally, apparently there are oscillations, and that's indeed true because I have one oscillation of the fundamental frequency, and I have another oscillation imposed on that of a lower frequency, of a modulated signal on top of it, right? And that's reflected in this phase, this local phase. I mean, we had FA as an analytic signal, and I now like to call this I like to make this equivalent to the bold-phased F introduced before, and I like to call that a time-varying phasor, the TVP for short. Yeah, so that is just a phasor that rotates in the complex plane, or in the real and imaginary signal plane over here, because that's, if I do the projection here, original signal, and the projection there will give me my Hilbert transformation. Just the same what we in the classical sinusoidal phasor case. Then if I project from here, then I got the cosine, and if I project from the imaginary part, I get the sine, and the sine is the cosine. Okay, so this is now the picture you have. Reflecting this time varying thing, time varying. We can go a little further, and we can look at this is rotating at a certain velocity, and this velocity is not constant in general. Only for purely sinusoidal waveforms, this velocity is a constant, and that's the reason why we can remove time out of the equations, because your phasors always move at a constant speed. So this information is irrelevant, right? But here it isn't. Here it is relevant, and what we can do is we can introduce what we call a local angular frequency, and I put it between quotes because it's like a generalization of frequency, and indeed it coincides for purely sinusoidal waveforms. It coincides with the frequency we know, but in the last couple of decades there have been a lot of discussions about these definitions, and especially about this name, because It's not really a frequency. I rather call it just the local. That's maybe much better. Just call it velocity, because that's what it is. This thing moves with a certain velocity. Yeah. Okay. The dot notation is the DDT. Yeah. By the way, don't remember if I already said that. So this is just how fast is the angle? How fast is it moving? Well, we can also do the other way around, and we can say, okay, if I read theta dot is omega, this is a differential equation, right? It's the d theta dt is omega. So that has a solution of this form, yeah, with some initial angle, starting at the moment that we press our stopwatch and start looking at the situation, or at the moment that we start measuring. So this is a solution of this differential equation, yeah. And additionally, we can also introduce a local radial velocity, and that is how fast is this thing like extending and like shrimping, yeah. So that I can measure as this rate. So I take the derivative, so the rate of change of the amplitude with respect to time, and then I normalize it by dividing with the amplitude, and let's call this sigma. Okay. So well, this also defines a differential equation, and that's given over here. Now we know theory of differential equations that this all and there, and then you see that you have equality. So this is a possible solution. And the reason for doing this is that written as an initial starting at the moment that we start measuring. Interesting. And what we see here is that actually S is now composed with well, if you remove t, the dependence of t out of this, what you get is just what we all have been learning as being the Laplace variable, right? But we have a major generalization of variable that is like normally we call the complex frequency domain, but now we also use time again. Okay. I can imagine that you have to digest this a bit because this seems very awkward. But I mean, what I said before, with mathematics, I can create anything I like, right? As long as I'm consistent and I'm following the rules, I'm following all the theorems of the mathematical constructions. That's what I did, and then I get this result. Well, let's see what you can. So that means that I can also define something like a local impedance. Because remember that also with the complex power, what we do is we average out everything what happens in the cycle. And that's also what we do with regular impedance. We remove time. I mean, that's the ultimate way of averaging over time, is just by removing it, right? Because it's always the same over time. So the average of something that's always the same is that thing that's always the same. But for distorted waveforms, it's differently. So now let's look at just an inductor. I just have an inductor, yeah, with the current flowing through it, and then I measure a voltage over it, right? That's what I do. A U of t, and I have an I of t. And suppose that the current, that somehow I can express it in this way. I come back to that later, but as amplitude and phase and frequency modulated signal. So distorted current. Well, this is what we know just from physics, okay? Just a Maxwellian relationship. then if I apply the analytical signal transformation, then I get this. So then the same law remains valid, because the only thing I do is that I add an imaginary part in terms of the Hilbert transforms, right? So I can just do that. I just have two equations, essentially, a real one and an imaginary one. And I can just compactly write that in terms of a single equation. So that holds too. From this, I can write this as a TVP, a time varying phasor. And then if I just do the math, so I differentiate this signal, then I get this long beast over here. What you recognize here, right, is that this is our omega. Okay? Because remember that omega is the derivative of the angle. Well, this is the whole angle, right? This is the whole angle. That's my theta of t in that sense. Yeah? So then this is what you get. And now if you define an impedance, which is just the ratio of two phases, of the voltage phasor in this case and the current phasor. So then I have this expression and I divide it by this expression. Yeah, then what you get is this. This is the local radial velocity, and this is your local angular velocity, which is your generalized Laplace variable. And we know that in the sinusoidal case, if you then do the Laplace transformation, yeah, then you have just z, which doesn't depend on anything, yeah, or is sigma plus j omega times L. And when you do Fourier analysis, then what you say is, okay, we take this thing, and that's reflecting the transient part, so the moving part in between a cycle, and extending even a cycle perhaps. And you take that to be zero, and then you get like your Fourier representation of your impedance, right? And that's when everything is in steady state. So this suggests that writing this, that you are in quasi steady state. I mean quasi steady state because things are moving about the fundamental, and that's reflected in this amplitude and in this time varying phase. And it's fluctuating about this part. Yeah, but it's not a transient, but there is a lot of stuff, there's more stuff going on than just a sinusoidal steady state. Because we're considering distorted signals here in general. But this is the idea. Now you can do the same thing for a capacitor. Yeah, then you just have the admittance as just the completely dual, and then you get this as a time varying or local admittance. Yeah, and if you do 1 over, you can do 1 over y of t. That gives you your z of t. Yeah, and then that's 1 over s of t times c. Then you have your impedance, right? This must be c. Okay, well, that's all mathematically sound. At least let me know if I made a mistake. But I mean, somehow this is simply too good to be true, or at least always be true for any given signal. And even if it's true, mathematically speaking, I mean, what can we do with it and how can we interpret it? And there are some issues. But let's first go even a little bit further. And let's suppose that at the point of common coupling, or at the ports of a network, we have these two time varying phases. Suppose we have these two general time varying phases. Then it's very straightforward to compute the time varying complex power, right? It's just the same operation. And then I introduce this tildes here just to differentiate or to distinguish the notation from P. Capital P is reserved for active power, and the capital Q is for reactive power. These things are now time varying, and I call this the real power, and this you can call the imaginary power. Yeah, but it's not exactly or directly related to the reactive power, as we know it at least. Of course, in the sinusoidal case, the dependence of time just drops again, because then these things actually, they represent moving averages when they depend on t, and they represent these mean quantities when they do not depend on t. And so I can also define a time varying power factor then, and I can even define a time varying apparent power. But notice that I put it in between quotes. I don't know how to call this. It's the magnitude, a time varying magnitude of your complex power, your time varying complex power. Okay, so that means that everything we did for purely sinusoidal signals, we can just extend almost verbatim to this time varying case. And here is what I did. Suppose I have an initial phase or just a phase of 0, and then I have a modulated in amplitude and modulated in phase over here. Then you can just redo the math, but essentially you just put the time dependence of t everywhere, like what we did before, and then I get this expression, in which I now have that the time varying real power and the time varying imaginary power, they are just given by these expressions. That looks very familiar, because in the sinusoidal case, everything just boils down to this again. And Q is this. Okay? So that's included. This is a special case of all that I'm introducing here as a function of time. You can also just avoid all these things and do a bit of math and then conclude that the real part is actually given by the sum of your instantaneous power, the original one, and you can call this perhaps its Hilbert pair, right? That's given over here. And for the reactive power, and this, people who are working with geometric algebra, for example, should recognize some thingies over here. That you have this skew symmetric property over here with the minus sign and the mix of these products. And so what you can already conclude from here is that this is always a local thing, because in order to define this, then I mean, I actually only need to know this. Yeah, this is just the product of two quantities which I can directly measure. This, on the other hand, are products of quantities that I cannot directly measure, because a Hilbert transformer, if you want to build it in practice, I mean, it's not so easy. I mean, it's an all-causal filter, so in general, you can only approximate it, and if you want to do it precisely, you first have to record the whole signal, and then the transformation running behind in that sense. But this also means that this imaginary part is not local, because you have a mix. This is local, and this you can, these things you can only, the Hilbert transforms you can only obtain afterwards, let's say. Yeah, so you need to have the whole measurement, so all the information, so the full history of your signal, in order to be able to compute the Hilbert transform. So this already suggests something that I don't want to go into details with at the moment, but that instantaneous power or reactive power theories, like the Akagi stuff, that cannot be true somehow, because instantaneous reactive energy cannot exist, and it's because of this reason, because of the non-locality of the Hilbert transform. Okay. Take the if it are periodic, if we are dealing with periodic signals, I mean, then you can just take the mean quantities, and then, I mean, taking a mean quantity of this guy over here, then you just get active power. And if you take a mean quantity of this, so you average just over a cycle, then by noting the asymmetry between those two objects, yeah, then you actually recover Booleano's reactive power as a mean quantity. And this, for me, years ago, was that I finally understood, at least for myself, what this reactive power of Booleano, which has had a lot of opponents. It was in the standard before 2010, and then it was taken out. And you have I think Czarnecki's most famous work is that what is wrong with Booleano's reactive power and why it should be abandoned. I mean, in my opinion, I mean these assertions are too much overstressed, and I think what we should really acknowledge is the fact that the Booleano's reactive power is a mean quantity. And of course, I mean, if you want to compensate something that is a mean quantity, then that doesn't mean for the distorted signals that you are doing a good job, right? Because you have to take everything that's going on within the cycle. You have to take that into account if you want to optimize things. But from here we can also conclude that Booleano is, of course, just a straightforward generalization of the UI sinus phi, right? And that's given over here. This is the way how Booleano defined it. And if you apply, if you take the average, or if you have these kind of signals, and then you set up your time varying imaginary power, and then you take the mean value over one cycle, and then you get this. For those two signals. And this is, of course, a straightforward generalization of this. So I'm not advocating the use of Booleano's reactive power here. I just like to show you that this is like it's merely reflecting a mean quantity. And on Wednesday, I will go a little bit deeper into the physics, and there I will show you that it's indeed also related to the imbalance between magnetic and electric energy. And so Booleano's reactive power does have a physical explanation and a physical relevance. The only thing that is perhaps doubtful if it's relevant for power factor optimization. But as a physical quantity, well, it is a candidate. But let's go back. I see that I talk way too much. Let's come back to that on Wednesday. Just a couple of things here for a resistor. So let's apply this time varying power triangle or power trinity, if you like. Let's apply it just to an ordinary resistor. Then you have Ohm's law. Analytical signal representation would be this. If you compute the complex power, what you get is R and then the amplitude squared as a function of T. And so that's this at least sticks to our a common notion that resistors that they only convert real power, because the imaginary power is 0 in this case. But now the interesting part comes if we do the same thing, but then for just a linear time invariant inductor, what we also did before, then on basis of its impedance. So we do the same thing, and then if you compute the associated complex power, then you get this. And you get this extra term. And normally, for purely sinusoidal signals, what we would get is just that S, not varying, not depending on time, is then J omega L, and then the RMS value squared. That's in the sinusoidal case. In the non-sinusoidal case, you get this extra real part. And now, if you use the fact that we had this let's say generalized or Laplace variable, or better maybe this local complex velocity or frequency, if you like to call it like that, then I can rewrite this in this way, and that is perhaps a bit more physically appearing, in the sense that this omega m, this Wm is just the moving average of the magnetic energy stored in the inductor. It's just the half Li squared, but it depends on T. And this is, you can, if you do simulations, you clearly see that it nicely averages just your moving signal. And so what you now see here is that we have this real part and this imaginary part, and using this S variable. So it's 2 times this S variable times your moving average of your magnetic energy. And remember, in the Laplace domain, that S, if you assume your initial conditions to be 0, then S with Laplace domain is the ddt, right? So that makes perfect sense. That this is actually a moving average, and 2 times the average gives you like a maximum value, right? And that is the S is just the let's say the time derivative of energy, and that's of course a power. But in contrast to the classical sinusoidal case, you now get this real part, and that's most probably why finding a proper, commonly accepted definition of reactive power is so utterly complicated. Because of a mix-up, a cloaking of imaginary and real parts. Because usually, and that's also what Czerneski is doing, for example, he defines reactive power as just as some kind of quadratic sum of all the imaginary contributions of your admittance, yeah, and then associated to each frequency. So some kind of like a quadratic sum he makes out of that. But it's only concerning the imaginary part, and to deal with the real part, he introduced this notion of scattered power. Well, this you can see as kind of a scattered power, if you like. Yeah, but now it's just purely in the time domain. Okay, and of course also, I mean, the charge and discharge of your inductor, that must come from real energy anyway. And I come back to that on Wednesday, because something weird with just the classical notion of reactive power is that functions like a perpetuum mobile or something. I mean, that oscillation is there forever. I mean, that cannot be true, right? But with non-sinusoidal signals, that appears already. You're already warned that some of the change must come from real energy, and that's dictated over here, or implied over here, I should say. Now the same with the capacitor, and then everything is dual again. So then I look at the complex conjugate of the local complex frequency, and I have an electrical energy, but it's the same thing. Only now it becomes minus. Remember that in the sinusoidal case we had Q is 2 omega, and then we had this difference, right? I presented in the beginning. So this is for capacitors, and then indeed we have this minus over here. Okay, and this is the complex conjugate, the star. Okay, well, I'm running a bit over planned time, but I think I'm almost finished, and then we can have I think we still have plenty of time for discussions. So I will go rather quickly to this, but just to warn you that it indeed sometimes it's too good to be true, all that I have been presenting, and I'm still puzzling about this, and I'm not the only one. Also in the signal processing community, there are a lot of questions. And that is, for example, illustrated over here. So I have just the sum of 3 sinusoids, so purely a sum of 3 purely harmonic signals. I just add them together, and then I define the local amplitude as I presented before. And the blue signal here is the original signal, and the light green one here, that's then the amplitude. Well, you tell me. I don't recognize any amplitude in this. Also in the local phase, well, that's of course a little bit harder to digest, but I cannot make any sense out of this. I mean, I cannot not see any relations with the nice amplitude modulated signal I presented before as an example where it does work, right? So here, mathematically speaking, everything is all right. And I can already tell you that if you take the mean values, you get exactly the right results that you can also obtain using other techniques. But in terms of the local interpretation, I mean, you have a bit of a problem here. Nevertheless, and that signal processing community is is very important. The skill again. We already saw that the economic skill, let's say the global skill, how power is generally measured, and that you already wipe away a lot of information there. I mean, here again, I mean, maybe now we have too much information that on each level has its own structure. So the question here is, what kind of skill and what kind of structure, or to put it together, what skill of structure are we interested in? And then, well, we have to go into filtering and stuff like that. And there are a lot of filters you can find in the literature, each with their pros and cons. And this is just to inform you and to warn you that straightforward applications of this analytical signal approach for general signals can lead to surprises, right? Although again, mathematically everything is perfect in that way. Okay, we can also like turn it around and then suppose that we have like a top-notch phasor measurement unit, and that we just measure a real signal like a voltage or a current, and then this PMU it demodulates for us this time varying amplitude and this time varying phase. Then the question is, given this representation, under what condition does the straightforward application of or let's say the straightforward construction of your analytical signal by just taking this amplitude and taking this phase and then construct your time varying phasor or your analytical signal like this is done in an unambiguous way. And what is known as the Bedrosian condition, and that was already known in the early 60s, the previous century. And that is, suppose that I have like a low pass signal called G, and I have a high pass signal called H. And now, if the spectral support of these two things is disjointed, so the low frequency overlap with the high frequency stuff in H, then we have that the product, the Hilbert transform of the product of these two signals is given by the low pass signal times the Hilbert transform of the high pass signal. This is the Bedrosian theorem, actually. And that's, I mean, this is if and only if, actually, but I mean, it's a sufficient condition to ensure some interpretations like a clear interpretation of amplitude and things like that. And if you apply this, of course, to our situation with the time varying amplitude and time varying phase, that means that if I take the Hilbert transform of my AM and PM modulated signal, then we have this. And then you can see that this part is indeed a perfect quadrature of this part, but it's only under this condition. Okay. Well, I'm almost finished now. I mean, there is one way to circumvent this whole Hilbert and analytical stuff anyway. The only thing is that I cannot guarantee whatsoever the validness of this approach. It all relies essentially on finding this P plus and the P minus. And in MATLAB, you have in the signal processing toolbox, you have this function called envelope. And it's there since version 2017 or something, if I remember well, which applies all kinds of spline interpolation process things, and you can tweak it with a number of samples. That's all numerical stuff, but then you can have estimates of your P plus and your P minus over T. So that's essentially just the envelopes of your instantaneous power profile. Yeah, and all the stuff I have been presenting for sinusoidal case, you can prove mathematically that it just simply goes over to this. It's just the same expressions, but now depending on time, and where I've introduced the tildes in order to differentiate from capital P, capital Q, and capital S. Yeah, but in the sinusoidal case, It's just the same thing. Only left with a few examples. This was the one, the first example I gave of this time varying conductance. If you apply this process, you can use the Hilbert transform. That works in this case perfectly. That's unambiguous, and then you can nicely track the amplitudes. But you can also, this is done using this envelope function of MATLAB, but it gives the same results. And then you see that this time varying power trinity now gives you a little bit of a different picture, because you see that the power, or excuse me, there is no imaginary power. I don't like to call this reactive power yet, or not at all actually. There is no phase shift, so there is no imaginary stuff going on. Yeah. But what you see is that then your time varying apparent power equals your time varying real power, and that means that your time varying power factor is 1. And this is what I like to call like a physical, whatever that means, but I mean, or let's call it something else than the economic power factor, which you can show to be smaller than 1. I mean, dealing with a resistive element, and I mean, there is no phase shift whatsoever, so the power factor should be 1. So in this way, we avoid stuff like distortion powers, which you can show using electromagnetic field theory. They simply cannot exist. It's nonsense in that sense. Here we don't have distortion power, and we have at least some resolution, right? Another example is a fluctuating phase. So I just have a sinusoidal voltage, and I have some device that shifts the currents, shift the current like continuously. And here it is modulated like this, and you can actually show that this function is periodic, and you have to invoke this Bessel function of the first kind, but you just get a Fourier series, an infinite Fourier series actually. And what you see then is, this is the picture. Sinusoidal voltage with a steady amplitude and a steady phase. And then you see that the current is constantly changing from lagging to leading, and then we're back to lagging and then leading. If you apply this resolution, what you see is in dark blue, you get the instantaneous power, just the product of the blue and the red one. And then what you see is that you have this, the green one is the time varying real power, and that is going from something positive to 0, and when it's at 0, then your time varying imaginary power is maximum, right? And then the mean quantity of the green oscillating thing, that is what is called the active power. And what you also see is that if you take the mean value of the red line, the imaginary time varying power, that is 0, of course. The power factor, that also makes sense in this case. Here you have maximum Q and minimum P, so there at this point it must be 0, right? And at this point you have maximum P and minimum Q, so there the physical power factor is maximum. And the average one, the one you compute just according to the standards, then is just the average of this guy. Yeah. Well, according to Budiano, the IEEE and current physical components, then this was the situation precisely. But what it doesn't detect, they all do not detect that you have this phase shifts going on. There is some reactive power, or imaginary power rather. Yeah? And you can also see that from the frequency domain that we had a sinusoidal voltage, and then the first component of your Fourier for the current is perfectly in phase with that voltage. So there is no Q according to CPC, to current physical components, and also not a fundamental reactive power according to IEEE or Budiano. Details you can see in one of my recent papers about this. And so at least with this method, we can detect something that goes on within the period, because that's what's happening. This reactive, or excuse me again, this imaginary power within the cycle is changing. Yeah, but if you average it over one cycle, that's over here. This is one cycle. Yeah, then it's 0. So you throw away too much information, in my opinion. This is a real life voltage sec. This is what I took from. Maybe you know this. You have this P cube stuff, right? P cubes. It's like little measurement units you can just put into your utility room, and a lot of people did that. And I will show you that later on in the week. That on all spots in the world you can just look at the power quality of institutions and some companies if they share their information on internet. Well, I took this voltage from there. It's just real life data, and if you apply it, then you see that indeed at the moment this sec occurs. A lot of strange things are occurring over here in terms of real and imaginary power, and also in terms of that the power factor drastically drops over here. But again, I mean, when you compute this using the norms and the standards, then they will just get like a mean value of what is really going on, or at least what might really be going on. If this mathematical model I just presented has some connection with reality. Again, I'd like to remind you of these words by Einstein. Okay. For the presentation, I mean, here you have some obvious remarks. I mean, I think one of the most useful ones is are these two. That we need to distinguish between an economic and physical power factors if we want to gain our understanding in the problem, and especially in between global versus local timescales. I mean, this one is perhaps the most important message you can take home from this presentation. Okay, thank you very much.